Good afternoon, good afternoon, good afternoon. And to our people on the West Coast who I see chiming in, good morning to you. My name is Dr. Calvin Mackey of STEM Nola, and I'm here today to do another STEM Illinois at-home session. Over the last 2 years, STEM Nola has been talking to the representatives from the University of Illinois to bring the model of the program that we've created in New Orleans to the state of Illinois on behalf of the University of Illinois. This is our third STEM at Home session. Thank you all for chiming in. And we're in the process of building capacity in Urbana-Champaign to make sure that the University of Illinois can bring STEM into the households, the community centers, the after-school programs all across the state. And I'd like to say thank you to Chancellor Robert Jones and his entire team at the University of Illinois that have made this happen, even during the midst of a pandemic. Again, my name is Dr. Calvin Mackey of STEM Nola, and we founded STEM Nola 7.5 years ago to expose and inspire and engage communities in science, technology, engineering, and mathematics. In the last 7.5 years, we've engaged over 70,000 young people, over 18,000 families, and over 1,500 college students that we hire as college interns. We've put over $1.2 million in the hands of college students that we've trained and deployed into communities across this country to engage our kids in hands-on STEM. And we started this because I had 2 young kids 7 years ago. They're 16 and 18 now. You know, they don't talk to me anymore, but when they was younger and we used to hang out in the garage, my son said, "Dad, I don't like science anymore. The teacher just talked to the board." And I said, "Boy, that can't be real because it's in your DNA." So we went in the garage and we started doing all these hands-on activities. And I saw the benefits that my 2 sons gained by doing these hands-on activities. And I realized then other kids needed this too. And we recruited engineers, we recruited scientists, we recruited companies and colleges and universities. And that's how we've built this model that now is transforming young people all across this country. We can't wait until this pandemic is over. And imagine this, the entire world is waiting for STEM to save it. I mean, this pandemic is a STEM issue, and the scientists, the mathematicians, the technologists, the engineers, the infectious disease doctors and researchers, everybody's working to try to get us to a point where we can get back to some sense of normality. That is the opportunity before us when we study science, technology, engineering, and mathematics. Now, parents, we want you all to know something. Young people, we want you all to know something. In the 21st century, you're only going to have 1 or 3 options. Either you're going to take something, break something, and/or make something. And if you don't have the skills and the education necessary in the 21st century to make something, like make a living, make a life, make a difference, that's only going to leave you with the 2 options that we see on the news every night, and that's to take and to break. And we don't want that for any of our children. We want you to participate in events like this and get exposed to phenomena and understand how phenomena work, understand nature around you so you can understand and explain things, but more importantly, so that when you get into the classroom and the teacher introduces physics and mathematics and all these equations, you're not scared because it's been demystified because you understand how it applies in the real world. Now, right now in the middle of this pandemic, what is happening is that companies are accelerating their move to automation. In the 21st century, either we're training ourselves from the neck up or we're training ourselves from the neck down. And if you're training yourself from the neck down, your competition in the 21st century would be the automatic machine, the robot. And literally right now, because of the pandemic and because of the loss of workers and because of, people couldn't show up to work, corporations are accelerating their move to automation, meaning that they're taking processes and putting computers and robots in place to do the work that otherwise humans would do. So we have to be prepared. We have to train ourselves from the neck up to be prepared to deal with automation that's coming down in the future. And I'm saying in the future, but really it is the present. For example, before me, I have my little friend. This is my little friend, Alpha. Alpha is a humanoid. A humanoid is a robot that tries to behave like a human. This robot, Alpha, a humanoid, was made by UBTech Robotics, one of the largest commercial robotic builders in America. And guess what? Alpha can do all the things, many of the physical things that human beings can do. Alpha can do push-ups. Alpha can show off. And like me, after I do my Peloton ride, Alpha takes her time getting up. And if you think you're gonna go out in the world and change the world as an entertainer, and you're gonna be Lil Baby or Dub Baby or you know, whoever these rappers and singers and dancers are, and you're gonna be Michael Jackson and Beyonce, and you're gonna twerk and you're gonna just change the world, you're gonna have competition because Alpha can get it going. Go Alpha. Go Alpha. Don't hurt them. See, Alpha has servo motors, and we can control these motors through coding and Wi-Fi, and we can get Alpha to do all these cool things. Do it, Alpha. Oh, don't hurt them, Alpha. Alpha can stand on her head and bust a split. You too can program Alpha to do all these cool things. And believe me, there are life-size robots like this today that are performing jobs and activities in corporations across America and the world. Give it up for Alpha. See, the funny thing about the robot is that this robot doesn't care who's gonna win the Super Bowl. This robot doesn't care who won the most gold medals. This robot doesn't care, you know, whether or not the Saints gonna be a good team or whether or not we're gonna have Mardi Gras. See, the robot works 24 hours a day, 365 days a year, you know, all year. And while we resting, while we taking off to go see mama, or while we going on spring break, or we on vacation, the robot is working. And that's the challenge. That is the challenge. Your competition in the 21st century for physical labor will be the machine. And there's a saying that says, any labor that competes with slave labor must suffer the consequence of that competition, meaning that slave labor is free. This machine labor is negligible compared to what a company got to pay you. So we got to make sure that we train ourselves from the neck up and not the neck down. Because if we train ourselves from the neck down, we're going to lose to the machine. But if we train ourselves from the neck up, we'll be able to control the machines and the robots. We'll build them. They will not dominate us. And that's the why. That's why we're here. That's why it's important for us to be exposed to STEM. To my young people in Peoria, what's up? To my young people in Urbana-Champaign, what's up? To the kids on in Chicago, I see you. Even we got Rockford, Illinois on. I remember when I was working outside of Chicago in Naperville, Illinois, and I used to go to Iowa sometime to visit a friend, and I used to hook that right there in Rockford. So Illinois has been good for me. Now, I'd like to bring up my friend, Will Patterson, who brought me for the first time 10 years ago, invited me to the University of Illinois to speak at a conference, and we became friends, and thus led to this partnership 10 years later to bring greetings on behalf of the University of Illinois. Will.
What's going on, Dr. Mackey? How you doing?
Good, brother.
You know, I'm checking me and you out both. We got this red on, so they're going to think I done flipped schools. Now I'm a Buckeye, you heard? So you got the red on too. So, you know, we got to go that way then with the program. You already know. So, and much like what you're saying, Dr. Mackey, this is so crucially important that you just talked about something in terms of what I studied a lot last week with Engineering Unleashed is creating value. And today's session with Buoyancy and Density is for young people to really get access to information that creates value in their lived experience. And so these STEM at home initiatives are so crucially important for families who are doing, DJ Stilke kicked off one of her robotics or her DJing programs yesterday, and the conversation I talked to them about STEM at home and passed out the flyers and just explained to the families that were there that we want you online. Our schools will want to come online and be part of this programming that's coming out of New Orleans. We're so excited about it in terms of how it's impacting University of Illinois and how we do our public engagement, and then how you pivoted again and created this massive opportunity for us to continue to build even during a pandemic. But much like you said, it's crucially important that we got all hands on deck in our communities to really figure out what's going on in these spaces. And that's where the University of Illinois is so happy to be able to provide these opportunities to our young people throughout the state. I was speaking with the librarian down in Belleville this morning, And he talked about he wants to build his whole library program around science and tech. So we're going to take the Hip Hop Express Double Dutch Boom Bus, and we're going to go down there and find out about his program and start seeding a new project. And so we'll get Belleville and East St. Louis on board as well. So I'm excited. Back in the mix with you, Dr. Mackey. I'm Dr. Will Patterson from the University of Illinois. Welcome everybody to the Buoyancy and Density initiative today at STEM at Home. Back to you, Dr. Mackey.
Thank you, Will. Again, we're happy to be partnering with the University of Illinois. Today, the topic of the lesson, which I forgot to talk about, was buoyancy and density. We believe what we've created in this model is a high-functioning STEM community. And a high-functioning STEM community is child-centered, so everything we do focuses on the K-12 kids, adult-governed. So that means that once we focus on the K-12 kids, we surround them with college students, our college interns, and then we surround our college interns with STEM professionals. So at this portion in the program, I'd like to introduce to you my friend Z. Smith. Z. Smith is the principal and director of sustainability and building performance at a local architecture firm, EDR. And Mr. Smith actually he's a graduate of MIT in physics, engineering from Princeton, and architecture from UC Berkeley. Now, eventually, when we get this thing really going in Illinois, we'll bring more graduates on from the University of Illinois in your community so you can see the assets and the talent right there in your community. Z, bring it on.
Hi. I just want to, I'll introduce myself a little bit and then set up the conversation for the fun part of all the experiments coming and try to connect buoyancy and density to things that matter to people in New Orleans and Louisiana and really around the world. Just to introduce myself, I grew up in the farm fields of Michigan and Illinois. I studied physics at MIT, electrical engineering and computer science at Princeton, and I have a master's degree in architecture from University of California at Berkeley. Today I work in New Orleans at Eskew Dumez Ripple. We're a roughly 50-person architecture firm, and some of my fellow colleagues here from EDR, Will Netter here, and Rylan Auburn have presented at other sessions for STEM Nola. So I want to talk about density and buoyancy. So just to go over what's density. Density is kind of how much you have in a given amount of volume. And so if we think about this to kind of illustrate the spectrum, imagine I had a cube. It's 1 foot tall, 1 foot wide, 1 foot deep. And that cube could be of air, of styrofoam, of wood, of water, of concrete, of steel, or of gold. Well, how much would that cubic foot weigh? Well, if it's air, it's less than 1/10 of a pound. Styrofoam's 3 pounds, easy to pick up and toss around. Wood, 26 pounds. If you're in good shape, you can do it. Water, that cubic foot is 64 pounds. Concrete, 146 pounds. Steel, 490 pounds. And gold, 1,206 pounds. Well, each of these was a cubic foot. And what we mean by density is we just say for that cubic foot, here's the weight and here's the amount of volume. So that's the same thing as that wood is 26 pounds per cubic foot, or water is 64 pounds per cubic foot. That's the typical way that we talk about density, is the mass, or here on Earth, the weight divided by the volume. So easy to remember, if I have a solid chunk of something, if its density is less than water, then it'll float. So, styrofoam at 3 pounds per cubic foot, it's a lot lower density than water. So yeah, it'll float. In fact, it mostly floats above water. On the other hand, wood is 26 pounds per cubic foot. It's about half the density of water. So a log you'll see floating in the water will typically be about half submerged. An iceberg, right? Ice is just a little bit less dense than water. Like it's a little like 10% less dense than water. So that's the source of that whole idea that an iceberg, you only see the 10% above the water that's floating, that there's this huge thing lurking below water. Now, in school, we're often talked about this famous Greek guy, Archimedes, who used density in a really interesting way. He worked for this king, and the king said, my goldsmith, I gave him this big chunk of gold to make my fancy crown, but I'm wondering whether he really used all the gold to make my crown. I know how much my crown weighs. It weighs the same amount, but I'm wondering if what he did was he mixed some, like maybe a quarter of that with some silver that's a lot cheaper. and kept that gold for himself. I want to know, did he cheat me or not? And so Archimedes goes, well, simple. Let's melt down that crown, and we'll measure how much its volume is. We know its density, and we know what the density of gold is. And the king goes, no, but I like my crown. It's really beautiful. So can't you find a way to test how much volume is in there, what the density of this crown is, without destroying it? And so Archimedes, I didn't know what to do, didn't want what to do, decided I need to think clearly. Maybe I'll take a bath. So he's lowering himself down into the bath, and he notices the water rises up as he lowers himself into the bath. And that's when he said, he spoke in Greek because he was Archimedes, he said, Eureka. And all Eureka means is, I found it. I found the answer. And the answer is that the amount of volume, no matter how crazy the shape of Archimedes or the crown, will be found by the volume of water that's displaced, meaning pushed out. So if you take a big cup of water and you fill it up right to the brim, and then you take some oddly shaped thing, in this case, a little tiny pear, and you push it down in the water, the volume of that pear is exactly the quantity of water that spills out the brim. And you can measure the volume of water that fell into that tray, or you can measure the weight of the water and just weigh it. Either way, because we know that the density of water is 64 pounds per cubic feet, you can measure the weight or you can measure the volume. Either way, you can tell exactly how much water came out and therefore what the volume was of that object. So wait a second, you said that things that were less dense than water float, but we know that steel is a lot more dense than water. So why don't boats sink? Well, the answer is boats aren't solid steel. If a boat was filled with steel, it would sink like a rock. Instead, boat has a steel shell and then a lot of air. And so you need the total weight and the total volume gives you a density. And the air weighs a lot less than water, is a lot less dense than water. So the combination of the air and steel makes something that is less dense. And the neat trick is, if you want to know how high or low the boat will flow in the water, it's that if you take the volume of the water, the weight of the water that gets displaced as you put the boat in the water, that's identically equal to how much that boat weighs. So how does that apply to life today? Well, here in Louisiana, we live a lot on the water, and there are all these great houseboats that are often towed we build them on land, we put them in the water, and we tow them to where we'd like to go, live in the bayou, do some great fishing. And these can get pretty fancy. They can be 2 stories, you can have a deck, all kinds of things. In the Netherlands, which is a whole country where half the whole country is below sea level, everyone loves living on the water, but of course they're on the ocean, so tides go up and down. So what they've done is they've developed a form of housing that there's these piers going down into the mud below the water, and then the whole boat goes up and down with the tide as the tide comes in and out. But we have another thing of concern with climate change. We're all concerned about bigger and bigger storms. And so during those storms, most of the time, it's going to be completely dry, but occasionally there might be flooding events. So rather than the flooding coming in and doing damage to our house, or having to make our house be up high in the air most of the time when we don't want to live high up in the air most of the time, what if we could make our houses, they could be kind of amphibious, right? A frog is an amphibian. He spends part of his life in the water, part of his life on the land. What if our houses could be amphibious? And so there's a whole project being done for all kinds of different countries, different parts of America and around the world, to make houses that can float, that can be amphibious, led by this project called the Buoyant Foundation Project that Elizabeth English drives. But we've already built some examples of these buildings. So here in New Orleans, there's this building called the Float House. It's built as part of the Make It Right Foundation, where this is a bunch of college kids, and they got together and they get these big honking chunks of styrofoam, and they drill out, they put all the power lines and the sewer lines and the water lines into that styrofoam, and then they spray on some thin, super thin concrete around it. And now you've got this floating object that's like incredibly strong. They put it on the back of a truck. They did this they were in Los Angeles. They drove it across the country. Here they are driving it right past the Superdome. They crane it into place and they build the house right on top. And so now you have a house that can float, but during normal times, it just can look like any other house just sitting right on the ground. So these are the ideas of how buoyancy and density show up in our lives in lots of different ways. So with that introduction, over to the fun stuff. Let's do a lab.
Yeah, where y'all gonna put it on me?
It's on you, guys.
Oh, all right. I was seeing something else on the screen. Welcome back. Thank you, Z. As you can see, what I love about Z is that he is passionate about buoyancy. On Fridays, I try to go fishing. Next week, I'm gonna bring y'all some picture of my fish. Last week, I caught a 40-inch, 40-plus-pound redfish. Amazing big fish. And I did release him back into the water. You know, he had lived a long life. Let him go back to his family, but I got the pictures. But you know, when Z was talking about buoyancy and density, the only thing I could think about was when I was going out to the Gulf of Mexico, and we're on this 22-foot boat. We're going through the intercoastal canals and all these big ships, and how we have learned to work with water. I got a PhD in mechanical engineering from Georgia Tech, a BS in mathematics from Morehouse. So mathematics and water have been close to my heart, and I hope today we do a great job of introducing you to buoyancy and density. Now, you've heard from Z, who's the professional. Next up, I will bring DeMarco Smith, one of our college interns, to take you through the sessions on buoyancy and density. DeMarco is a Baton Rouge native, way of New Orleans, and then eventually moved to Baton Rouge, but now he's a chemistry major at Xavier University in New Orleans. And he's in a 3-2 program, and that's what I did. I went to Morehouse for 3 years, got a mathematics degree, and then you do 2 years at your engineering school, and I did mechanical engineering at Georgia Tech. Well, DeMarco's doing 3 years at Xavier in chemistry, then he would transfer to Louisiana State to get his BS in chemical engineering. So DeMarco Smith, our college intern. DeMarco.
Hey guys, I'm DeMarco Smith. As he said before, I go to Xavier University. My major is chemical engineering and chemistry. And today we'll be doing buoyancy and density. So I'm pretty sure you guys can be real familiar with buoyancy and density. How many of you guys know about boats and submarines? For instance, like a submarine, once it goes underwater, it has like little air pockets in there, which allows water to go inside to sink. So that's something you can use for buoyancy and density. That's an example. So let's jump into the agenda. Topic introductions. We're going to do vocabulary terms. We're going to have activity instructions. We're going to do adjectives, activity questions, and then the activities for today is going to be making edible boats and Cartesian Diver. So for example, this is a Cartesian Diver. This is how it's going to look. So when we squeeze it, it's going to have to go down and come back up. Like say for instance, if a diver jump in water, now he goes down and then come back up for air. So let's get into the experiment. Vocabulary words. For instance, we have density. Density is how close together the molecules of a substance are, or how much mass a substance has given in space, having a given space. The next vocabulary word, buoyancy, is the upward force that a fluid exerts on an object less dense than itself. Next vocabulary word, water displacement, occurs when an object is largely immersed in a fluid, pushing it out of the way and taking its place. For instance, guys, you guys remember I told you about the submarine with the air pockets? And in this example, we have the boat. So as you guys see, the boat have air pockets in it, and that way it allows water to go inside just a little bit, enough so that it can be able to sink and balance. So we want to reach an equilibrium. So that's an example. Last vocab term is Archimedes Principle. I always like to say Archimedes, that's how I remember it, but it's Archimedes Principle. States that the weight of an object submerged in a fluid is equal to the weight of a displaced fluid. So, you guys ready for the experiments now? The adjective, density. You will understand the meaning of the terms density, buoyancy, water, displacement, and Archimedes Principle and apply them to the project correctly. You will make an edible boat in Cartesian Diver, as you guys seen. Cartesian Diver, squeeze it, goes down. So objective questions. What are we experiencing with today? Rockets, wind, or buoyancy and density? I'll give you some time, guys, to think about it. That's correct, buoyancy and density. Questions of the day. So guys, keep these questions on your mind as we do the experiments. So remember, guys, first question is, what is buoyancy? Remember, what is buoyancy? Keep that on your mind, okay? Next question, what happens to the pressure inside of the bottle when you squeeze it? That's the next question. Keep in mind, that's a big question. So keep in mind, once we do the experiment, pay attention to all the facts, okay? The last but not least, what makes a bottle float in water? Next question. Okay, so first experiment is gonna be edible boat. So first thing first, let's go get all your materials. What you need, you can use a nutty butter or Oreo cookies, a pretzel stick, food coloring, airhead, plastic knives and utensils, a plate, and small mixing container. So I'm going to use a cup for a small mixing container, have pretzels, Oreos, and I have icing and blue food coloring because I wanted my icing to be really blue. And don't forget, you're going to need utensils. As you guys see, have a plastic knife. So while you guys go run around the house to get the experiment, I'll tell you the science behind it. The hull is the shell of the boat. The main sail is the large sail that captures the wind power that is needed to move the sailboat. It attaches to the mast, which is a large vertical pole. This pole is also attached to the boom, a long pole parallel. As you guys see in the picture. Next question. What makes a boat or ship float? The air that's inside of the ship is much less dense than the water. This is what keeps it floating. So remember, guys, what makes a boat or ship float? The air that's inside of the ship is much less dense than the water. This is what keeps it floating. Remember, guys, when a ship is in water, and gravity pushes it downward, and the amount of water that is equal to the weight gets displaced. So remember, guys. So let's jump into the experiment. You guys ready? So first things first, we're gonna grab Oreos. I'm gonna use Oreos instead of Nutty Butters. I don't really like peanut butter much, but Oreos are best. We're gonna grab one first. So this is gonna be the base of our boat. Next, we're gonna grab some icing. We're gonna pour half the tube. I have a tube, just pour some in the cup. And I'm gonna do 2 drops of food coloring. Then I'm gonna use my utensil. And we're gonna stir. Check it out. It's blue. So basically the blue icing can represent the water. So this is water, basically. And we're just gonna smear it all on top of the Oreos. You wanna make sure it's kind of thick layered, so that way when our sailboat is placed on top, it can be able to stick and sit there. Make sure it's real nice and thick, guys. Check it out. The next step, we're gonna break out Oreo in half. As you guys see, it represents like a little boat. You can choose any side that you want to. Once you break it in half, open one side up. Grab some icing, pour it inside. So we're using white icing inside. So that way, so we didn't use the blue icing because we didn't want water to be in our boat like that. We want to give the illusion that it's still a nice boat and not drowning or anything like that. And we put icing in it so that way it can be able to hold better. So you can just place it right on top. Make sure you place it on top and in the middle. Next step, you get a pretzel stick and an airhead. So the pretzel stick is going to be used as the pole and an airhead is going to be used as our flagship. So keep in mind your airhead is maybe still a little hard, so you guys can either put it in some warm water, like a bowl of warm water to loosen it up better. But since I don't have that right now, I'm just going to use this and just wrap it around the pretzel stick. We're going to just apply reinforcements to the boat. For instance, I'm going to do it just like this. And we're going to place it right here at the back of it, kind of. And voila, we have a boat. You guys want to turn it to the front camera? Oh, the flag fell. Hold on. It's okay, guys, if you experience a little trial and error, we're trying to stabilize it. It happens all the time. Check it out. And most importantly, since the boat is edible, you can eat it. Now, keep in mind, if you're allergic, make sure you ask your parents first before eating it. But if you're not allergic to anything, go ahead and dig in. Oh, yeah. There's a lot of icing, guys. So I'm just going to put this to the side. And then we're going to move on to our next experiment. So remember, guys, clean up your area. If you need any napkins, take the time, go get napkins, wipes, anything to make sure you get your icing up. Okay, are you guys ready for the next experiment? So the next experiment is going to be Cartesian Diver. So for this experiment, you're going to need one straw, one water bottle. So if you have a water bottle, get a water bottle. You can just take the label off so that way you can have a full view of everything. And 2 paper clips. So while you guys are going to look for this around the house, I'm going to read the signs behind it. Okay, guys? So first thing first, what's the signs behind it? When you squeeze the sides of the bottle, you are increasing the pressure of the liquid inside. So you remember what I said, guys? You squeeze the bottle, it goes down, then goes back up. So when you're squeezing it, it's increasing the pressure that's inside the liquid. That increase inside the pressure is transmitted to every part of the liquid. That means you are also increasing pressure on the straw itself. Squeeze it hard enough and you will push some more water up and inside the straw. The air inside of the straw squeezes tighter as more water is forced in. When you squeeze the bottle, the air bubble in the straw compresses, gets smaller, and that makes it more dense than the water around it. When this happens, the straw sinks. When you stop squeezing, the straw gets bigger, and when the water is forced out of the straw and the straw begins to rise. So remember, guys, when you squeeze it, it goes down. And we release it, it goes back up. So when you squeeze it, the straw gets smaller, but when you release it, the straw gets back bigger and it goes to the top. So now that you know the science behind it, let's get into the experiment, guys. So first thing first, your water bottle. Grab any water bottle around your house. It could be Dasani, Ozark, Core, anything. And then you're gonna need 2 paper clips and a straw. And don't forget, you're gonna need some scissors to cut the straw. So, first thing first, we're gonna cut the straw. So I like to compare my straw to previous straws. We're gonna cut about, let's see. It's about a good, this straw is gonna be bigger, so we're gonna do about 6 inches. You guys see? Now we're gonna fold the straw in half. So make sure it's in half, guys. It can be like this, like a V, create a V. Once you create the V, you're gonna grab your paper clip. And you're gonna put one end of it inside one of the straw holes, and then the other end of the paper clip inside the other straw hole. Just like that. You guys see? I'm gonna do it one more time for you guys. Take the end of this paper clip right here. We're gonna take the end of it, put it inside. Then the other one, I'm gonna put it inside too as well. Just like that. Then once we finish, we're gonna grab the other paper clip. We're gonna open one side of the paper clip up. You guys see? I have it open just a little bit, and we're gonna hook it to the paper clip that's onto the straw. Voila. So I'm gonna do it one more time for you guys. Paper clip. And here go the paper clip with the straw already on it. I'm gonna open it a little bit. We're gonna put it into the paper clip. Voila. So now we're gonna have to open up our water bottles. And remember, you can put it any way. I would prefer just to put it down like this, have the paper clip hanging down. So once you have it hanging down, just push it in and voila. So the trick is to push it down, make sure it's like submerged under water before putting the cap in. And let's check it out. So remember, guys, squeeze, squeeze, squeeze. As you guys see, we created a Cartesian Diver. So do you guys have any questions so far about anything? No? Any questions? So remember, guys, the question I told you guys to keep in mind from the beginning, first question is, what is buoyancy? What is buoyancy? That's the first question. Is it the downward force of an object that keep it stuck to Earth? Or is it the upward force that acts on an object in the air? Or is it the upward force of a fluid exerts on an object less dense than itself? Is it A, B, or C? You guys got it right. It was the last answer. It's the upward force of the fluid exerts. Next question. What happens to the pressure inside the bottle when you squeeze it? I'm pretty sure you guys know this one really well. Does it decrease, increase, or stays the same? What happens to the pressure inside the bottle when you squeeze it? Does it decrease, increase, or stays the same? You guys got it right. It increases. Last but not least, what makes the boat float in the water? Now, you guys should get this one. I believe in you guys. The air in the cell, the air that's inside of the ship is much less dense than water, the water inside of the boat. The answer is the air is inside of the boat. Inside of the ship is much less dense. You guys are really, really smart. So you guys have any questions for me so far? So guys, after you guys finish your experiment, please make sure you send us pictures. Go to webinar@stemnola.com and email us your pictures. And please be on the lookout for us next Tuesday, August 17, 2021 at 4 p.m. Central Time. We will be doing experiments on wind, guys. Thank you guys so much.
Yeah, DeMarco, he's taking my stuff. That's what I'm supposed to say, DeMarco. Y'all give it up for DeMarco. Give it up for DeMarco. Saying my stuff. And the reason why I want to say it is because, let me take my mask off. And we're wearing a mask because we're still in the middle of the pandemic. And I know you all are dealing with the fourth surge also. And people believe me, this is serious. Parents, masks do work. My PhD is in fluid mechanics, how things flow. If you Google Calvin Mackey, or you Google Calvin Mackey and mask, or you Google Calvin Mackey and Forbes.com, I've written articles for Forbes on the history of masks during pandemics. Over 100 years ago, when we had the influenza pandemic of 1918, masks were politicized. People argued over masks, and that was the only protection they had then. But also, we've made a video where we demonstrate literally the barrier method that masks provide, right, in terms of what can flow through the different types of masks. So we are STEM Nola, and we believe in science, technology, engineering, and mathematics, and the science wins out. Now, thank you all again. Send pictures and videos, send pictures to webinar@stemnola.com so we can show our sponsor, University of Illinois, that you all actually participated and that this is something that you want. Now, I know that many of you all in Illinois, all of you all in Illinois are definitely on Central Time, and we're on Central Time, and we know school has gone back in. My son started school on Monday, and I know that many of you all are starting school this week or next week, so we will shift our programming time to 4 p.m. Central to accommodate the fact that you all are back in school. So if you're in an after-school program, or if you're in some other like out-of-school time event, if you homeschool and you need some science, 4 p.m. Central, we'll be here to deliver that to you. Also to school districts, you can use this in your programming for your 21st century programs, trio programs, boys and girls clubs. We are here to serve you. Thank you all. You all have a great day. My name is Dr. Calvin Mackey, and we'll see you all next week at 4 p.m. Central. STEM Illinois at home. We out.